So, as Simon said, the theme I've chosen for my series of lectures is mathematics and its links between culture and creativity. The first 3 lectures of this year are going to concern the relationships between mathematics and music, and today it's musical composition. So, if you want to know how to write a piece of music using fractals or magic squares, or if you want to know what links music and polygons and matrices and clocks, then keep watching. Well, music's developed in all cultures, and it's taken perhaps different paths and developed along different forms in different cultures. Today, the focus for me is going to be on the Western classical tradition. That's purely because that's been the basis of my own musical experience, but there are fascinating stories to tell in other traditions too, and in the transcript that will follow this lecture, I've put a few references there at the end if you're interested in exploring some of those parts. To describe some of the lovely symmetries of music and the ways in which mathematics can be involved, I need to begin with just a very brief primer on some of the notation around music. So don't worry if you're not an expert in music, I'm just going to give you a brief overview so that we can have some common language here. So first up then, I've got a picture here of a picture of a piano keyboard. The key thing here, pun intended, is that there are 12 different notes that make up an octave. So if you're a group of people singing in unison, feels like you're all singing the same note, actually, usually the men in the group will be singing an octave lower than the women and the children. And so these notes that are an octave apart have this special relationship with each other, and they have the same names there. You can see a C here and a C here. Those sound similar to us. Now, in the Western tradition, the octave is divided up into 12 equally spaced pitches, and these are divided each by a semitone. So I'll just play you might be able to hear. There's the 12 notes of the octave. They each have a different name. The smallest gap between them is a semitone, and 2 semitones make a tone. I'm showing you now a couple of semitones. Oh, I'm showing you the octaves now. So C goes to C, so those notes are an octave apart. And we can also have, inside our octave, what's called the diatonic scale. So just the white notes on the piano, if you play those, what you get if you start from C is the scale of C major. This scale can be moved up or down wholesale, any number of semitones, to create other scales and other keys. So your starting point is the key that you're working in. So I'll just play you the scale of C major, which I did earlier. There it is. So those notes in that arrangement with those gaps of a tone, so semitone tone, so this is a tone, another tone, then a semitone because there's no black note in between, they give you the diatonic scale. So that's what the notes are called. How do we write down music? So some of the symmetries that we're going to be talking about involve how music is written down. It all started many centuries ago with this chap, Guido d'Arezzo. He was an Italian monk, and he was kind of getting frustrated that the choristers were not able to learn the complex new melodies quickly enough, because until then, what you had was neumes, which is you take your psalm or whatever it is you're learning, and above them, there were sort of indicative swooshes, and if the swoosh went up, that means that your voice goes up. But of course, you can't learn a melody exactly from that. It's more of an aide-memoire. So Guido d'Arezzo invented staves, which are these horizontal lines, and they tell you exactly where the note is, what its pitch should be. The next step was the mensural notation, which tells you how long your notes should last. So I'll just briefly mention this here, and to note, I know that some of the people watching online are based in the US, where we have different words for these notes. So in the middle here, a crotchet is what we call it in Britain, but in the US it's called a quarter note, which begs the question, a quarter of what? And it's a quarter of the thing on the top, which in America is called a whole note, and in Britain we call it a semi-breve. That's another question. Yes, it is half of a breve, but we don't really use breves much in music nowadays. So a semi-breve is 4 crotchets. A minim is 2 crotchets. A crotchet is a crotchet. Then you can get half of that and quarter of that by adding little tails onto the stems of your notes. So you can have quavers and semi-quavers and demi-semi-quavers and hemi-demi-semi-quavers until you get tired. Already you can see there's something mathematical happening because these are kind of powers of 2, halving and doubling the whole time. Of course, we're not restricted just to having notes like that. You can do all sorts of other things. So you can have triples. You can put dots after your notes. So it's another bit of infinite sequences here, I guess, going on, because if you put a dot after a note, you add half its value again. So a dotted minim would be 3 quartet beats, because half a minim is 1. And then you could put another dot and add half again, get 3.5 beats. So if you had infinitely many dots after a minim, you can decide how many beats you think that would be. I don't think anyone's ever actually done that. If you're quiet temporarily, which I'm not often, then you can have a rest. And so you indicate how long you're not playing your instrument or singing for with particular symbols that indicate that. And finally, on the kind of rhythm front, often pieces of music will have a broader rhythm to them where you group together notes in what are called bars, and the first note of each bar is accented. So you might have a march, do, 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 where the first of every 2 beats is accented, or waltzes, which have 3 beats, and so on. So we've got our durations and our rhythms. We know what the notes are called. How do we put them onto these staves? So here are the notes again. There are different choices you can make depending on what instrument you're working with, but I've got the treble clef here, which is indicated by this symbol, and there you can write down the notes of the C scale, the white notes on a piano, just by starting at the bottom here. That's our middle C that we heard earlier, and then every space and every line consecutively is just the next note up. Now you can put the in-between notes, the black notes, into this notation, and what you do is you use these symbols. Sharp means it's a bit higher, it's a semitone higher than F in this case, and alternatively, it's flatter than, it's lower than G. So this note here can be called F sharp and G flat equally well, and so you write those on the stave like this. This means we have to be a little careful when we're making geometric analogies, because the same note can be represented in different ways on the stave. So we'll have to just take care when we get onto that. And so then, now we've got the notes, we've got the durations, we can write our music. So let's talk about some of these musical symmetries. I'll introduce them fairly quickly, and then we can get on to some of the mathematics around it. So the first thing you can do when you're writing a piece of music is repetition. So of course in songs you can have verses and choruses, the tune of the verse will repeat, and the tune of the chorus will repeat. And you can have repetition of phrases, you can have repetition with a delay, like in a round like Frere Jacques or Row Row Your Boat or something, where one voice is delayed following the others. And of course then the trick is they have to sound nice together with each other. This particular example is from a lovely piece of music called Ceremony of Carols by Benjamin Britten, and this is from the carol This Little Babe, and it begins with all 4 parts are singing in unison the same thing at the same time, and then every verse, one part will just break off and delay a bit before starting. So by the end, you've got this same tune being sung by 4 different parts, with each one with a delay of a beat, and it's a very good effect. I advise you to listen to it if you have not heard it before. So you can repeat things. The next layer up is you can repeat, but you can shift the notes up or down a bit. So Beethoven's Fifth, everyone knows that. You've got your da-da-da-da, and then you repeat it, but you shift it down a tone, da-da-da-da. So this is called translation, where you shift up or down some number of semitones or tones. What else can you do? Well, you can reflect. So there's this thing, inversion, which you can think of as reflecting in a horizontal mirror. So I've just got there, if anyone's had to learn the piano, has had the joy of learning the piano as a child, or still does now, these contrary motion scales are where the right hand's going up and the left hand's going down. My piano needs tuning. Okay, so you can see visually, it's a very clear thing, you can see it looks like a reflection. Okay, there are examples throughout music. If you want an example of anything, go to Bach. That's my rule in life. So here it is a fugue by Bach. In the first 3 bars in the right hand, you see this particular melody or phrase, and then it's repeated but inverted later on in the left. And I've put them on top of each other just so you can see. This is an exact symmetry. So if you can reflect in a horizontal mirror, of course, you ought to be able to reflect in a vertical mirror, and you can. That's called retrogression. So I've got just a couple examples here. So the bottom one here, this is from a Haydn minuet, and the first half is just reflected backwards. I should probably make it too small now to see the individual notes, but perhaps you can see the shape is reflected. And so this retrogression, or playing in retrograde, means just play it backwards. There's a nice, of course there's one in Bach, obviously, but there's also a nice example from the 14th century in a rondo called Ma fin est mon commencement, my end is my beginning, and that's for 3 voices, and the top voice and the bottom voice are the reverse of each other, and then the middle voice is the reverse of itself, so it's a palindrome. So that's quite nice. Now, the things we've seen so far, they have the property that you can define them without having to rely on the particular choice of notation. And that's something we really need in mathematics. We don't want to rely on how we write the things down. We want whatever we're doing to be sort of impervious to any changes around that. So these things, translation, inversion, retrogression, we don't have to rely on the stave. The stave, you see, has an implicit bias in favour of C major, a particular scale, in favour of the white notes on the piano, because those are the ones you can write down without adding any extra symbols. So it means that what looks like the same gap between 2 notes, if you write them on the stave, depending on what the notes are, can actually not be the same gap if you move everything up 1 line or something, because you might gain an extra semitone from one of the black notes on the piano. So it's important to choose, if we're trying to do mathematics here, to choose things that don't depend on our choice of notation. Now, there is another example of a symmetry which does depend on the physical artifact of the score. And I wanted to show you it because it's quite fun. So, sort of rotation, question mark. We can take a piece of music and written on a score. An example here is Der Spiegel, the mirror, written, well, attributed to Mozart. We're not absolutely certain. Now, this has a property that what you do is you take this piece of music, you and your friend, who are violinists, you face each other across the table, you're both looking at the same piece of paper, but of course you're seeing opposite sides of it. And then you play, and it's a duet. So your finale is your friend's beginning, but upside down. So if you see it rotating, you can see that there is a different tune coming out, and the skill here is to make them both sound nice together. And that is very difficult to do. There's one in Bach as well, of course, from his musical offering. As I say, everything is in Bach. If you want a more recent example, you can listen to Ludus Tonalis by Hindemith, and this is from 1942. And this work is full of symmetry, large scale and small scale. The whole thing is symmetrical, so there are 25 movements. They are symmetrically arranged. There's the prelude and the postlude, and in the middle there's the interlude, and then movements sort of coming into that central interlude alternate with being fugues and with being other things interspersed. So there's all sorts of symmetry going on, and a lot of these compositional tricks and devices about inversion, retrogression, and so on. But in particular, the postlude and the prelude are the rotation of each other. So that's quite nice. There is a little last joke, though, a last tonal game that he plays, because right at the end of this completely reversed and rotated prelude that gives you the postlude, there's suddenly an extra C major chord to finish. So that's kind of a last joke that he plays on us. But I was listening to this the other night. It's a good listen. So these structures and these devices are used quite a lot by many composers over many centuries. What I want to talk about is some of the mathematics behind it. So we've got these ideas of inversion and translation and so on. I want to use the words of a predecessor of mine, not as Gresham Professor of Geometry, but as Gresham Professor of Music, Yannis Xenakis, who was Professor of Music from 1975 to 1978. And he was a very interesting guy. He had trained in engineering and architecture and had done mathematics, and then Messiaen advised him to bring mathematics and all that he'd learned into music. So he did a lot of mathematics in his music, and we'll talk a little bit later about one thing that he did with probability. But he said music then is steeped in the problem of symmetry, and symmetry is made accessible by the theory of groups. So if you're paying attention to the introduction, you will know that I am a group theorist, so of course I like this sentence. What is music, if not very often, a set of structures made from the permutations of notes and of sounds? So we're going to explore this theory of groups a little bit. I'm going to give us some ground rules. So we have to focus on the interval preserving transformations. And we don't want to, if two things are an octave apart, then whatever symmetry we're going to do, we don't want them not to be an octave apart afterwards. So that's why we're going to focus on those. We want to avoid our implicit bias towards C major, because we don't want to create any favouring of particular notes over others. So we don't want to explicitly look at reflections in terms of the physical reflection in a stave line or something like that. We're going to define these things in terms of what they do to the pitches and the semitones rather than the visual image. And we will measure all our intervals. So the interval is just the gap between two notes, right? We'll measure all of those in semitones, not in terms of notes on a particular choice of scale. So that's our kind of ground rules. So what is this thing that we can call a translation if we want to stick to those ground rules? Well, let's have a definition. We'll just say, we'll call it Tn. Tn will be translation up through n semitones. So the example I've got there is just a pair of notes, and they are both being translated up through two semitones. Up, up, there we go. So that's just two steps, and we're just marking equally on that little graph there. We're marking our semitone lines. So this isn't a stave or anything. So translation up through two semitones, fine. Well, we can do other things. Let's now translate down through three semitones. And you will see that the net effect there is that our original thing has gone down by one step. So we went up by 2, down by 3, and the net effect was down by 1. And 2 minus 3 is indeed minus 1. And this always works. When you combine these things, if you translate through n and by m, then the net effect is you've done a translation through m plus n. There's a couple more points to make about translations. First, there is the boring translation through 0 semitones, i.e. you leave everything identically where it is. Because it's identically where it is, you call that the identity map. Just leave everything where it is. The other thing is that if you go through 12 semitones, now we heard earlier that 12 semitones make an octave. So actually you get back to the note you had before, just in a higher register. And we've said we consider those to be the same sort of notes. In unison singing, we still think everyone's singing the same thing. So going up 12 semitones really isn't doing anything in terms of what the music, the pitch classes are of the music. So we're going to think of up through 12 semitones as really not doing anything. It's the same as our 0 translation, the identity map. And because of that, the kind of arithmetic we're doing with these translations is a bit like a clock. You know, when we tell the time, if it's 2 o'clock when I finish, 12 hours from then, it'll be 2 o'clock again. It'll be 2 o'clock in the morning, not 2 o'clock in the afternoon, but it's still 2 o'clock. So translations also satisfy this clock arithmetic property. And to remind us of that, so to remind us that if we do translation through 7 and then translation through another 7, that's not 14, it's now 2, because with octave, we just discount. So to remind us of that, we use a symbol. We just put a circle around our plus sign to remind us of the fact that really we've got a clock going on. Another point is that, so we can have this rule that when we add together two translations, we just add the amounts and that's all fine. Then there are exactly 12 different translations, because once we get up to 12, we're sort of back to 0. So there are 12 different translations. This is one of the things, of course, we like to do in maths is count things. There are 12 translations, and we can make any of them just by taking translation through one semitone and then repeating that as often as we need to. So we've got these 12 things, and all of them can be made by just our favourite translation that's just, we'll call T, through one semitone. Okay, so that's translations. Now let's think about inversions, which is a little trickier to understand initially because where you put the mirror matters. So we've said inversion is like reflection in a horizontal. But where is your horizontal line? It does matter. So I've got a couple of examples there showing the same phrase but inverted in two different ways. So we need to understand what the possibilities are there. The position of your mirror matters. So what actually are we doing when we're doing inversion? Well, if you imagine a particular pitch, and I've got one there, I've chosen this note is called G sharp. It gives you a symmetry in the piano keyboard. It's the middle of the three black notes there. So you have this sort of visual symmetry, but you could pick anything, any pitch. And if you're going to reflect around that pitch, what you want to do is you take your pitch P, and if you've got some other pitch, and I guess you're measuring these things in semitones above some default level of 0 that you've decreed, you take your pitch P and you have at some other pitch X, and to reflect in that pitch P, you just want to bring it to the other side of that pitch, but the same distance. So if you're 2 semitones above that pitch, the image, what you end up with, ought to be 2 semitones below. So just like a normal reflection. So how we do that is we say, okay, if X is here, and you're reflecting about this pitch, the distance from x to p is x minus p. So if you take that off, you get to p, and you take it off again, you will get to the other side of p, the same distance. So the expression for it is just, if your inversion, we call it IP, about a pitch p. You take your x, and you subtract twice x minus p. Simplify that, 2p minus x. So that sort of gives you an expression for where my pitch goes to, and the image of that under that transformation. Okay, so again, I've got a favourite inversion. You can pick your favourite inversion, but we just decide on one, and a particular pitch that we will say is pitch 0. And then everything else can be measured in terms of how many semitones above or below that 0 pitch is. So, you know, I've picked G sharp because of aesthetic reasons, basically. But anything you like, say that's 0, and then I will call I will let that be inversion around that pitch. And the reason that's kind of the most useful one and the easiest to deal with is because if you decree that your p there, your pitch is 0, then this inversion, well, 2p is 0. So you're just sending x to minus x. Okay, so that's my favourite inversion. Now, it turns out you can express all inversions in terms of that favourite one and a translation, a carefully chosen translation. So why is that? Well, you can see the little calculation there. What are you doing to your pitch x here? Well, you do your inversion, which sends x to minus x, and then you do the translation through 2p to it, and that adds 2p. Just moves up 2p semitones. So the net effect is 2p minus x. Hooray, that's exactly IP of x. That's exactly my inversion, IP. So that tells you that, in fact, every inversion can be made with your one favourite inversion, I, combined with a translation. Okay, so there are 12 inversions, that means, because how do you make them? You take your favourite inversion and you combine with one of your 12 translations. So there are 12 inversions. So we've got 12 translations and 12 inversions. What's next? Retrogression. That's playing it backwards. So you're reflecting in a vertical mirror, in some sense. So we'll call this R for retrogression. And now we've got three things: translation, inversion, retrogression. And you can say, well, all right, can I combine these? Can I do a translation, then an inversion, and then retrograde, and then another translation, and so on and so on? There must be loads of things I can do. Well, after a fashion, there are, but there are some rules that govern the way these things interact with each other, and I've written three of them there. So the example here shows that retrogression, playing it backwards, followed by inversion, is the same as inversion followed by retrogression. You can check this out for yourself, but it doesn't matter which way round you do those two things, you get the same outcome. We say in maths they commute with each other. So that means if you've got a big expression with lots of R's in and lots of I's in, you can move all the I's to one side and move all the R's to the other side because they can just move past each other. And it's the same thing with retrogression and translation. You can just swap them over in any expression. It's almost the same thing with inversion and translation. The rule there, which you can sort of check the algebra if you want, but the rule says, okay, if you've got my thing and I do the inversion and then I translate it up through n semitones, that's the same as if I translate it down through n semitones and then do my reflection. You get the same outcome. So that means you can move your translations past your inversions, but at the cost of changing a few plus signs to minus signs. So that tells you that anything you can make from these R's, T's, and I's can be written in exactly one of the following ways. It's either a translation or it's an inversion. There are 12 of those, 12 translations, 12 inversions. Or it's, we call all these retrogression, but a translation combined with retrogression. And there are 12 of those because there are 12 translations. Or it's what we call a retrograde inversion, backwards and upside down. Okay, so there are just these four types of things. And it can be shown that there's nothing else. So these are all definitely all the things you can make starting with retrograde, inversion, and translation. There's nothing else. These are the only interval-preserving transformations, the only things that leave octaves an octave apart, and all the other intervals where they should be. So there are 48 things. There are 12 of each kind. And these 48 things form the mathematical structure known as a group. And it was, at least in part, it was this that Yannis Xenakis was talking about when he was saying we understand music through group theory. So I want to tell you a little bit, at least give you the definition of a group. There are lots and lots of examples of groups all the way through mathematics because groups measure symmetry. So anywhere you have a symmetry, there's a group lurking in the background. That's why they're such powerful objects. They're also nice because they can be defined in just 4 rules. So it's not a huge, complicated edifice. There are 4 rules that tell you whether a set is a group. And it's all about how the elements are combined. So a group, it's a set. So for example, we could take the set of whole numbers, integers, or we could take the set of our 48 musical transformations. The key thing is that any pair of elements in that set can be combined in some way with some operation such that the outcome is still in your set. So the set is closed, we say. You can't escape from it by combining elements. You will always get something back that you already have. So we've sort of alluded to this already with the music group, which I'll call M, I guess, for music, that whenever you combine these retrogressions, inversions, and so on, you do get back something you already have. So I'm going to show you 2 groups side by side and just tell you the other rules that apply with groups. And all of these are there for very good reasons, that they allow us to prove fantastic things. But all groups have these same 4 rules. And that means if you prove something about a group in general, then you've got something about all these different situations. So one is whole numbers, and another one is the music group, but there are all sorts of examples elsewhere. So, okay, let's have side by side these 2 examples. So integers, whole numbers, how are we combining them? By adding them together. And with the musical transformations, how are we combining F and G musical transformations? Well, we just do one and then we do the next one. So what's FG done to your X? X is any old pitch. Well, it's F of G of X. Okay, so the first rule is this closure rule. You have to be able to stay inside your set when you combine any 2 elements. So for whole numbers, certainly if we add together 2 whole numbers, 2 integers, the answer is another integer. So that's okay. And for our musical transformations, well, if you've got 2 things that preserve intervals, then if you do one of them, the intervals are all still preserved. And then if you do the next one, you're still preserving the intervals. So the net effect of both of them will still preserve intervals. So that's okay. Okay, the next thing is a kind of a technical requirement, but it's about how you simplify complicated expressions. So with addition, it would say if you've got 3 numbers, A, B, and C, then if you want to find out what's A plus B plus C, you get the same answer if you go A plus B plus C, or if you go A plus B plus C. Same answer. I don't know, kind of, we all know that implicitly from doing adding up from our earliest years. The same thing happens with the music thing, that if you do F of G of H, it's the same as F of G of H. Okay, so that's just something we just have to check. And it works. The next thing is, we've already mentioned with music, you have to have this element of the set that doesn't do any damage. It just leaves everything where it is. This is called the identity element, just like we had the identity translation, where you just leave everything where it is. We're not doing any damage. Combining that with any of the other interval-preserving transformations will have no effect. And this is the same with the number 0 when you're doing addition. You know, any A plus 0 equals A still. So adding 0 has no effect. Translating through 0 has no effect. So that's called the identity element. And that relationship of having no effect comes into play when you have other elements of the set and you have this sort of undoability property, which is the idea of inverses. Now, I apologize that inverse is a very similar word to inversion. The thing is, they're both such deeply rooted concepts in the respective areas that I didn't want to introduce either of them by using a different word. So inverse is not the same as inversion. We'll just have to manage for the next minute or so to get past that. So what is an inverse? Well, it's kind of the undoing of an element. So with addition, if you add A, how do you undo that? You take A away again. And so A, take away A, is 0, your identity element. So every element in your set has to have this idea, it has to have an inverse, you have to be able to undo what you've just done. This happens in the music group as well. Everything is undoable. So if you translate up through 6, then you can undo it by translating down through 6. So that would be its inverse. How about if you do an inversion, a reflection, a horizontal line? Well, if you do an inversion and then there's the inversion, then you do it again, you're back to where you started. So inversion is its own inverse. So maybe it's not so bad that the words are similar. And retrogression. reflecting the vertical line, playing it backwards. If you do the retrograde, and then you do it again, you get back to where you started. So those things are their own inverse. So everything has its own inverse in the music group. So these things form this mathematical concept called a group. Now, I said there are groups everywhere in the world and in mathematics. Actually, the music group itself has echoes elsewhere, in geometry and in other places. And I wanted to just give you just a couple of those echoes. And when I'm talking about echoes, what I mean is there are some subsets of this group that themselves form groups. So they are closed in this way that we discussed. And those things are called subgroups for obvious reasons. And there are 3 of them that appear in disguise elsewhere in life. And I've got you just sort of indicative pictures here, which we'll see what's going on. So the first one is we've already seen this idea of a clock. So a clock group, we might have 12 hours in our clock, but you can have any number of hours. Our translations, the set of 12 of them, form this group where when you add things and you don't, if you get to 12, you loop back to the beginning again. So you can call this the clock group, or mathematically it's called the cyclic group. Luckily, the same letter C is involved in both cases, so you can choose which one you prefer. There are infinitely many of these things. So our clock group that crops up in music is when the clock has 12 hours, but there are other kinds of group that have this property. So another example is something like the days of the week, where, say, 7 instead of 12 is the magic number. 7 days after Monday, sadly, it's Monday again. So we have this same cyclicness. So that's the clock group, and there are lots of those, infinitely many, in fact. The next one is to do with geometry. So if you take the translations and the inversions together, that's 24 elements, they have the same relationship with each other as the symmetries of a regular dodecagon, 12-sided polygon. And the way you sort of translate, overusing that word, from one setting to the other, is if you think of translation up through one semitone, you convert that into rotation through 30 degrees, or a 12th of the way round. And you convert inversion into reflection in the horizontal line. If you do that, and make all the products and things that you can, you precisely get the symmetry group, the group of all the possible symmetries of a dodecagon. So there's some geometry. And then the final thing, this poor woman is doing what we're supposed to do every few months. We're all supposed to turn our mattresses, right? I don't know how many of us, anyway, I'm sure I do it, definitely. Sometimes. So here, I like to think of this as the mattress turning group. It's got a proper maths name, which is the Klein-4 group. So we can think of this little subset of the music group as the mattress turning group, because these are the ways in which you can turn your mattress. So you can leave it where it is, that's translation through 0. You can flip it top to bottom, that's like inversion. You can flip it side to side, that's like retrogression. Or you can flip it side to side and top to bottom, which my hand can't do, and that's retrograde inversion. And those are the 4 things you can do with your mattress, and that forms a little group. So there are some examples of the echoes of music in other areas of mathematics and life. Well, you could ask then, this is fun to find the mathematics behind the music, but does this stuff get used? Are people using these mathematical symmetries and the knowledge that there are 48 of them and so on in music? Are composers using this stuff? And the answer is yes, of course, otherwise I wouldn't have asked. And to see how, or one way in which that's happening, we need to meet Schoenberg and his 12-tone method. So he was one of the key proponents, and then the second Viennese school came out of this. There were others around that time. In the early 20th century, there was a lot of exploration into how we can move away from your key signature, so your C major or your whatever key signature you've got. And if you're doing that, you don't want just to have nothing. You want to have some structure, but what structure are you going to replace your key signatures with? And one answer is tone rows. So the idea here is your piece of music, you don't have a key signature, you just have a row with each pitch class, each of the 12 notes that you can have in an octave, appearing exactly once in a defined order. Okay? Now, only the pitch class matters, so you can go up or down as many octaves as you like. It's easy to see. The C comes third in that list, so that's where it's going to be. Now, you get pretty boring music if you're only allowed to repeat these 12 things in that order all the time. So in addition to that, you're allowed to transform your tone row of 12 things, but only using interval preserving maps. These 48 transformations that we've talked about. And the reason for that is that the interval preserving maps will then ensure that you always still have 12 distinct pitch classes in your row of 12. So Schoenberg explored this idea, and I've got an example here from his suite for piano, which was the first work composed entirely with tone rows. There's the theme, there's the retrograde. Even if you don't read music, you can see that this, is the reflection. We've got the inversion of the theme, which is a reflection like that, and then the retrograde inversion. So you've retrogressed the inversion. There's one kind of cute thing I want to mention about this, but you need to know a bit of German musical theory. Not very much, because I don't know very much. So in German musical notation, the letter B actually stands for the note B flat. And then what's B natural, what in Britain we'd normally call B, that's denoted by the letter H. So if you look at the first 4 notes of the retrograde theme here, if you can read music, you'll be ahead of me. It goes B, A, C, H, Bach. So Schoenberg has a little homage to Bach in his suite for piano. And lots of composers do. Bach himself had a few Bachs in his work. That's fine. Okay, so of course we want to say, how many tone rows are there? That's our natural question. How many scales are there? There are not very many. There are 12 different pitch classes, and there are some variations of this, but you either can have a major scale or a minor scale in each of those keys. So 24 possible key signatures, for Bach to use in his well-tempered clavier or everybody else using. So there are more tone rows than that. How many? Well, there's 12 choices for the first pitch, and 11 choices for the next one, and 10 for the next. So you have to multiply all of those together, and you get 479 million. Now that's a lot. You're not going to run out of tone rows. But remember, if you picked your tone row out, you are allowed to use any of the 48 images of it under these translations and inversions and so on, the 48 elements of your music group. So there's not really 479 properly different ones, because you can use any of those 48 images in your work. So I really want to know how many really different ones. It can be my starting point. It's not just divide by 48. You might think, everything's got 48 images, so put all those 48 together, and that counts as one, so just divide by 48. The problem with that is illustrated by a Webern tone row. So he was, one of Schoenberg's pupils. I'll call it W, this tone row. He put 3 Bachs together, or at least this is a Bach, B flat, A, C, B natural, and then he inverted it, and then he did a retrograde inversion. So this tone row of 12 different pitches has 3 Bachs in it. It's got some internal symmetry, though, because he's done the inversion and the retrograde. That means that some of the images, some of these transformations, take our W back to itself. They fix it. Right? In particular, this one, I, T minus 1, R, takes W back to itself. So it does not have 48 separate images. It's got fewer than that. I think it might be 12. So that means we can't just divide by 48. So what are we going to do? We can't go through 479 million tone rows one by one, working out how many images they have, and then ticking those off our massive list of 479 million things. That's not going to keep anyone sane. So of course, group theory comes to the rescue. And in particular, something called Burnside's lemma. This is William Burnside. He was professor of mathematics at the Royal Naval College in Greenwich in the Victorian era. And there's a result called Burnside's lemma, which I want to tell you about because it precisely deals with this situation. Okay, so I'm going to talk you through what the lemma says. So you have a group, we have a group, it's our musical group. And the group is doing something, it's permuting the elements of some set, X. So in our case, our musical group is permuting all these tone rows. Okay, now we're interested in not the total number of tone rows, because some of them are equivalent to each other. We can get to them using elements of our group. Our group is moving them around. So what we really care about is the ones that are the same as each other in terms of you can get between them by using these transformations. So if one thing is a translation of another one or an inversion, we want to think of them as the same thing. So we'll say that the elements of your set are in the same class if they're mapped to each other by some element of your group. So if you move between them using the transformations in your group, then they're the same as each other somehow. Okay, so in order to state this result, I need this little tiny bit of notation. You take something in your group, say you might take, I don't know, retrogression, and you write this term fix of that group element, little g, to be all the things in your set, all the tone rows, for example, that are left where they are when that transformation acts on them. So we saw an example of this with the Webern tone row. It was fixed by some particular transformation. So that particular tone row would be in this set, fix of that I t minus 1r. Okay, so you work through the elements of your group, and there are only 48 elements of your group in this case, not 479 million. So you've reduced your calculation to 48 rather than 479 million, which is a good bit of reduction. And Burnside's lemma says the total number of different classes of elements of your set, so our tone rows that properly are different, is given by this formula. Okay? So what you do is you add up all the sizes of these fixed sets, you get a big number, and then you divide through at the end by the number of things in your group. So we would divide at the end by 48. So we won't go in detail through this calculation. I have put a bit more detail in the transcript if you want to look at it, or if you want to do it yourself and then check you're working. We've made a big time saving. Instead of 479 million calculations, we do 48 calculations. And a lot of them are very quick, because if you think about some row of tones, any translation apart from translation through 0 will change the first note and every note. So translation through, one semitone will move the first note up one semitone. So it definitely does not fix that tone row. It doesn't leave it where it is. No non-trivial translation fixes anything. So empty set, there's nothing there. So all of those 12 things are zeros, and lots of the others are zeros as well. Okay, so we can do this calculation, and the outcome, I can reveal, is that there are 9,985,920 tone row classes. So still quite a lot to play with. I don't suppose they've all been yet used. So if you want to go out and compose a bit of music with a tone row, there will be one for you that no one has used. Okay, so that's a little bit about this music group. Now there are lots of other ways that mathematicians have used musicians have used mathematics consciously in their work. And I want to spend some time talking about that in a moment, but I just want to leave you with this thought about how far can this be taken. So Pierre Boulez wrote a piece called Structures in 1952. In that piece, every single component of the music was defined by prescribed rules. So he had a tone row, and that it had 48 images. And this defined the notes he was going to play, but he also defined which order he would play the translations of it through formal rules and formal structures. He also defined the note durations, the dynamic instructions, and the mode of attack. Is it staccato, is it legato, is it loud, is it quiet? Everything was predetermined. And he said later this was kind of almost something he felt he had to do to almost work it through his system. So he said he wanted a blank slate, a tabula rasa. He felt that he was himself a small and very, very primitive computer. If he could have put it through a computer in 1952, he would have done. And he said this was a demonstration through the absurd. So this was taking the thing to its limits. And it was too structured, and there wasn't enough room for the composition really to happen. He was asked, would you like to listen to it again now? And he said, I don't feel the need to do that just now, thank you. But he said, it's something I really had to do. And he moved back from the total serialism after that point. So other ways then that composers have used mathematical forms in a conscious way. This picture here is of Kaya Sariaho, who will appear when we mention fractals in a moment. But there are just a few, I'm sure there are many other ways that mathematics can be used. There are a few ways we're going to talk through in the last 10 minutes of our time. Okay, so sets and groups. We've said something about groups, but I didn't want to move on before mentioning Milton Babbitt, because he's an American composer who's a pioneer of electronic music. He's the only composer that I know of who also has a theorem associated to him, Babbitt's theorem. So I will explain this very briefly. It says, given any set of tones, the multiplicity of occurrence of a given interval in the set determines the number of tones in common between that set and its translations by that interval. So that's a bit of a mouthful. Let's try and break it down a bit. So basically, you take a set of tones C, G sharp, whatever, a set of tones, doesn't have to be 12. And between each pair of those, there will be an interval. So the interval from this note to this note will be, 6 semitones, and the interval from this one to this one. So you measure all the possible, you take all pairs of tones, and you look at the intervals between them. So that's the collection of intervals. And then you say, okay, for example, maybe an interval of 5 semitones occurs 3 times in all this collection. That tells you that if you shift the whole thing up by 5 semitones, it will intersect your original theme in exactly 3 places. So how many times your interval occurs tells you the size of the intersection. So then you can sort of say, okay, are there sets of tones that have the property that there's the same number of occurrences of each interval? So every interval should occur like twice or something. Such things are known in mathematics as difference sets, the same number of occurrences of each difference. And they will intersect, if you're doing it in terms of music, they'll intersect all of their translations the same number of times. So you can sort of think about what's possible here. I'll just as an indicative starting point, I will say you can't have all 12 intervals appearing exactly once. And the reason for that is that the tritone interval, that's half an octave exactly, must appear an even number of times. Okay, so there's a Babbitt's theorem, so I thought I must mention him. Magic squares, I love these. So in magic squares, there's an example in this picture by Dürer, a very famous woodcut, Melancholia, of a 4x4 magic square. It's a square of numbers where the sums of each row, each column, I did the columns, each column, and each row, and the diagonals are the same, this constant number. So the British composer Peter Maxwell Davies used magic squares in some of his works, and in particular one called A Mirror of Whitening Light, where he processed, and we'll just say what that is, a Gregorian chant through a magic square somehow. And then the composition used this magic square and paths through it in various ways. So the square he used and the initial chant he used were 8 tones long. So that's a bit big. So what I've done in honor of today's lecture is I've created a composition myself, which is based on a 4x4 magic square, this one, and of course then I need a theme, or a little phrase of music that has 4 notes in it. So I have processed Bach through Dürer. So let's see what happens. I'll show you the method. So the method is you take your initial theme, your little 4 tones, so I've got Bach, and then you make the other rows of your square. By, say, the 3rd row, you translate your initial theme such that the first note on the 3rd row is equal to the 3rd note of your theme. Okay, and you do this for the other rows, so you translate by whatever you need to translate by. And so then you get a 4x4 square. And this isn't a magic square yet, but this associates to, so you just write the numbers in order, 1 to 16, and that associates to each number from 1 to 16 a note or a tone. So here, for example, 16 will be associated with this note, which happens to be a C. All right, so then you take your magic square. Here's my Dürer magic square. We know which year it was made, 1514. And you now have a path through your music, because this tells you that the first tone of your composition will be 16. And we know we've got a crib sheet, 16 is C. And the second one is 3. And 3, that's another C. And then you just work through the square. So you've processed this through. And there is the amazing first sight of this thing anywhere in the world. And if any composers are watching and would like to use this theme, you are welcome to do so. So that's Bach processed through Dürer, and it gives you a sequence of tones. You can't hear a magic square. But what this is doing, and all of these things are doing, are giving the composers a structure, a framework within which to compose. And, some amount of constraint is a boost to creativity. We don't say sonnets are too restrictive a form. It helps us create. So all these things, they are giving you a structure to work with, magic squares and everything else. Okay, infinite sequences. So I apologize to any Danish speakers watching. When I tried to pronounce the name of this composer first time, I got it wrong in at least 4 different ways, which is quite impressive because it's only 3 syllables. So this is Per Nørgård, not Nørgård. I apologize. All these years I've been saying it wrong. But he has used what's called an infinity series, or that's what he called it in much of his work since the 1960s. So what's an infinity series? So it is an example of something in mathematics that we call a recursive sequence. And it's based on a recurrence relation, so-called. The most well-known of these kinds of sequences is the Fibonacci sequence, 1, 1, 2, 3, 5, 8, 13, and so on, where each term is the sum of the previous two terms. So it's recursive because the next term in the sequence depends on earlier things in the sequence. Now, Per Nørgård's sequence is defined by a little bit more of a complicated set of relationships than the Fibonacci sequence. I'll just show you an example of it here. But you can make subsequent terms, and you make them in pairs, by looking at the previous two terms and then adding or subtracting the interval between earlier terms. So I've just given a little example there where you're starting with B and C, and you just generate all these tones. And then this can be used in your music. And probably the most well thought of example of his work is the Second Symphony, where you get, it's not this exact sequence, it's another one, but he uses an infinity series, and you hear it in various parts of the orchestra at different speeds, so slowed down or sped up, and you just sort of keep hearing echoes of it throughout. So that's an infinite sequence defined with a recursive relationship. Next up, fractals. So there's a birthday cake on this slide because Kaija Saariaho, her birthday is the 14th of October, and I'm giving this lecture on the 13th of October, so that's tomorrow, so happy birthday, Kaija. She has used fractal music generators in some of her work. I mentioned Nymphaea from 1987 for string quartet and electronics. She said, you know, some of this stuff is computer calculated and the motifs gradually convert, recurring again and again. I also know their greatest living composer, this was coming out of a poll in BBC Music Magazine a couple of years ago, where they asked composers to give their top 10, and then they made a big overall list, top 10 of all time, and of course it had all the Bachs and the Mozarts in. You could ask me at the end what the top 10 was, but she was the first in the list that was actually still living. So she is officially the greatest living composer. Here's a fractal. What's the thing about fractals? So this is the Mandelbrot set. The defining characteristic of a fractal is self-similarity. So as you zoom in and in and in, you get the same pattern repeating over and over again at smaller scales. So we can do this with sequences, actually, and that's what, I'll just let it get to the next Mandelbrot set. There it is. Okay, so the fractal music generators that I talked of involve fractal sequences, and you can use those in various ways in your composition. Notes, note durations, pitches, dynamics, whatever. I want to give you an example of a fractal sequence. This one's called the 2 Morse sequence, and you make it by, you start with the numbers, 1, 2, 3, 4, 5, and so on, and you convert them into binary. So in binary, something like this, 1, 1, 1, it doesn't mean 111, it means 1 lot of 2 squared, 1 lot of 2, and 1 unit. So that would be 4 plus 6. 4 plus 2 plus 1 is 7. Okay, so these are the binary numbers. And then what you do is you go through those and just add up the number of ones, add up the digits. Okay, and you get this. You get 1, 1, 2, 1, 2, 2, 3, 1, 2, 2, 3, 2, and so on. Okay? So there's 1, 1, 1 is giving you that 3. So what? Well, see what happens when we just pull out alternate terms of this sequence. Okay, starting from the second term. So I've just tried to highlight those there, and if we read those off, 1, 1, 2, 1, 2, 2, and so on. I'll just pull those out and put them separately, and here they are, and if you notice, this is exactly the same sequence, back again. This sequence contains itself at a smaller scale. And of course, you could pull that same trick with the subsequence here, and pull out the alternating terms of this, and you get the same sequence again. So this sequence contains itself infinitely many times at smaller and smaller scales. So it's a fractal sequence. This is the kind of thing that Kaija Saariaho has used in her music. Okay. Probability and randomness. So I've got 2 people to mention here, one more modern than the other. So Yannis Xenakis, our old friend, we'll just mention him. So he created the piece Achorypsis using a probability distribution. So it's something called the Poisson distribution that models rare events. And coming out of that, we have this formula that says if the average number of events per unit time is lambda, so say how many traffic accidents there are per month on this busy road, it's 3 or whatever, then you get a probability that a given event will happen k times in that unit time. So you could know if there are 3 traffic accidents on average, then what's the probability that there will be 10 or 0 in that particular time period, using this formula here. So what Xenakis did was to say, well, my music will be governed by this distribution. So he divided his performance up into cells of time, and he said, okay, how many of those will have exactly 2 events? So he had to put in some value of lambda, and then you can work it through, and it says that there should be 19 cells that have 2 events. So then he put his events in. Now, this is where the creativity, the events he calls in his book clouds of sound. So I don't absolutely know what that means, but that's what they are. The final thing is very modern probabilist, Joseph Haydn. You can own a unique Haydn minuet, your very own. This on the top here is the name of a game that was brought out in about 1790, and the makers of this game said that Haydn had written all the music in it. What you do is, so the game came with 16, for each of 16 bars, there were 6 choices, apparently all written by Haydn, and then you roll a dice, or a die, and in the third, if you have a 3, then you pick bar number 3, then you roll a 5, so you get bar number 5 here, and you go along, and at the end, you've got your own unique Haydn minuet just for you. Now, do we need to sue these people under the Trade Descriptions Act for an infinito numero di minuette tria? How many minuette tria really are there? It's not infinitely many. We can be very angry because there are 6 choices for the first bar and 6 for the second and so on. That would be 6 to the power 16 choices. So there aren't infinitely many. There's a big number, but not infinity. And it's worse than that because actually some of the bars are the same as each other. In the 8th bar and the 16th bar, there's a bit of repetition going on. Someone got a bit lazy, Mr. Haydn. So actually, if you work it out, there are only 940 billion minuette trio. So it's very disappointing. So that's a sort of an early use of probability, perhaps not in composition really, but I thought it was fun to mention. So I'm going to finish there, but just with a comment. This is a picture from one of Xenakis' books on how he wrote his glissandi, by saying all this is in aid of the music. As Schoenberg said, my works are 12-tone compositions. They are not 12-tone compositions. The maths is helping the music here, and that's as it should be. Okay, thank you very much.
Thank you very much for a dazzling start to your professorship. That was absolutely tremendous. And you won't be surprised to hear there are quite a lot of questions.
Excellent.
And I'll start you off with an easy one. This is more of a sort of musing than a question, perhaps. And this is a man called Chris Bevan and a couple of other people ask, they wonder whether Bach was good at maths.
Well, you see, I don't know how much formal instruction Bach would have had in mathematics, but that part of your brain that is good at maths, I think is very close to that part of your brain that is good at music. You know, he had such an instinctive grasp of symmetry, and you can see it. You know, a Bach fugue is just a thing of perfection and joy. So I would say, no, he's not doing group theory, but he is doing mathematics.
Is translation in maths the same thing as transposition in music?
Yes, so you're right, this is a good point. Is translation the same as transposition? Normally, I would say, and I can be corrected on this, of course, transposition might be when you're transposing a whole melody to sing it in a different key because, you know, the singer likes to sing lower or higher, something like that. So transposition to me is something you do to an entire composition, whereas translation might be just for an individual phrase that you're playing lower or higher within the piece of music. So that's the distinction I make, but it's the same sort of idea. Really, I would say transposition is translation of the whole melody.
Here we have a slightly more musical question. What about a stretch? Crotchets become minimums, etc.
Yes. So there's augmentation and diminution of the theme. I didn't mention that, it's true. I focus more on the, I guess I would call them the spatial transformations rather than the temporal transformations. But you're right, that could also be thought of, and that certainly would preserve intervals. I suppose my focus today has been on what I would call the spatial ones, but yes, those are certainly valid transformations that you could do.
Here's a specific question. How does the maths stroke geometry of John Coltrane's Circle of Fifths fit in with these other mathematical musical approaches?
Circle of Fifths. Well, goodness me, if you are free on November the 17th, we will be talking about Circle of Fifths, perhaps not John Coltrane's Circle of Fifths, but this is a common thing in music that if you move up through perfect fifth intervals, and if you do that 12 times, and then if you move up through octave intervals and you do that 7 times, if you do that on a piano, though, that gives you back exactly the same note. But if you measure what's mathematically happening to the frequencies, it's a tiny bit different. And that paradox is what we're going to spend about 20 minutes talking about in my next lecture. So tune in on November the 17th.
Great, that's a fantastic plug. Okay, so here are the 2 most popular questions that have been asked. How important do you think it is that the structure of a piece of music should be intelligible to the listener at first hearing?
This is a great question. I mean, if we think about what we're saying, the magic squares used by Peter Maxwell Davies, nobody, maybe there is someone, I don't think anyone listening to that for the first time would have been able to say, I think there's a magic square in there. Or if you're listening to acaripsis, can you detect a Poisson distribution? To my mind, it doesn't matter if you don't spot that on the first listening. It's one of these things, if you understand the structure behind it, I think it can add to your enjoyment. But if you don't spot it, or don't know that it's there even, you still, I think, can detect in some sort of subliminal way, just like in Bach's work or Mozart, there is a structure there, and it's giving a framework. So all of this stuff, I would say, if you're listening to a piece and you're enjoying it, and the composer has created this work, that's the key thing, that's the main thing, and the mathematical structure can enable that, and it's fun to understand it, but you should just enjoy the music.
This was a question asked quite early on in your lecture, and I think it's partially been answered, but not entirely. How have some composers incorporated the golden ratio and Fibonacci numbers into their work?
Yes, so you do get people either deliberately including the Fibonacci sequence and the golden ratio, which is connected. So the Fibonacci sequence, if you take ratios of successive terms, you get closer and closer approximations to this number, the golden ratio, which is also seen to give you the kind of most beautiful sort of rectangles and beautiful images and spirals that you can make from it. There are composers that have both used this consciously in their work, but also people have, in the analysis of composers' work, detected Fibonacci sequences. Now, some of that I'm less sure of. For example, you get people saying, 1, 1, 2, 3, 5, these are important intervals in the scale, and then 7 is important, but we'll just ignore that for some reason I'm not really specifying. And then 8 again, that's a Fibonacci number, hooray. And 13, well, that's the 13th note if you play 12 tones, 12 semitones, and then the next one is 13. It's a little bit kind of numerology-like sometimes, I think, people trying to fit the Fibonacci sequence into the numbers involved. But certainly composers do it on purpose sometimes. But yeah, I think that sometimes perhaps people have read a little bit too much into the accidental coincidence of many Fibonacci numbers appearing.
Just before we end, there is someone here who's asked something that I'd actually quite like to know as well.
Okay, excellent.
Most people wouldn't be able to hear music just looking at the stave and notes.
Yeah.
I wonder if mathematicians see music they listen to in mathematical formula equivalents.
Ooh. Well, I would say I'm quite a visual person. I could sometimes almost feel that it's a geometrical structure that's going on. If I'm listening to, you put on the Goldberg variations or something, or you're listening to a Mozart sonata, and something in that is so perfectly structured that it gives you the same happy serenity as seeing a beautifully carried out theorem and its proof. So I think there's, as I say, the same parts of the brain I think are engaged in that way. So I'm not sitting there going, aha, an integral when I listen to music. But I think you see it visually in the score, and you hear it go sort of deep into your soul in the same place where mathematics is kept.
Professor Hart, thank you for a really brilliant inaugural lecture. Could you just tell us when you're next speaking so we can all inscribe it into our diaries indelibly? Absolutely.
So my next lecture, which of course you can watch online as you are with this one, is on November the 17th, and the title is The Sound of Mathematics, and really we're going to be exploring the mathematics of harmony. So what makes some sounds go appealingly together? Why do different instruments playing the same note not sound exactly the same? And for a final little teaser, what can Galileo's father tell us about tuning a lute? So thank you for listening today, and hopefully I'll see you next time.